Here we stand on Earth, each morning greeted by a bright sun. We are just as sure that it will set today as it will rise tomorrow. What if we weren't so sure of this? Imagine that the sun suddenly vanished. What would happen to our planet? Would we immediately go flying off into space without the sun's gravity to pull us into orbit? Or would something else happen? Well, the answer involves the speed at which information can travel through the universe. In this case, the speed at which the information of the sun's disappearance travels to reach Earth. According to Einstein's theory of relativity, the effects of light and gravity from the sun take about 8 minutes to reach us. So, if the sun were to disappear in this instant, we would unknowingly continue our orbit around an empty point for 8 more minutes, deceived by the light emitting just before the sun's disappearance. During those 8 minutes, we would still see the sun's light and feel its gravitational pull as if it was there. Only afterwards would the Earth fly off of its orbit. This delay is governed by 2 principles. The first is relativity, which says that nothing, including information, can travel faster than the speed of light. The other is locality, which states that an object is only influenced directly by its immediate surroundings. This was the accepted understanding of physics in the early 20th century, until quantum mechanics emerged with a startling proposition. It predicts that particles would be able to communicate across infinitely vast distances. This scenario is obviously at odds with the principle of relativity and locality that we just outlined, and it divided physicists for decades on the unresolved question of how the universe really works at its most fundamental level. In order to better understand how quantum mechanics violated this principle of locality, it is first necessary to understand the principle of entanglement, a new kind of state unique to quantum mechanics. In such a state, a group of particles can exist in such a way that the state of one particle cannot be described independently from the state of the others. To illustrate this principle more clearly, let's say that we have a pair of magic dice. These dice are like any that you'd find in a board game, for example, but with one magic property that they share. If one dice is thrown, then the other will always land on the same number when it is thrown. The results of these dice being thrown are thus correlated to one another, and in this way, the dice are said to be entangled. To further illustrate the strange behavior of our entangled dice, let's say that we give our dice to 2 physicist friends, one named Bob and one named Alice. Before anyone even throws their dice, every number has the same probability of being landed on. In quantum mechanics, this is known as a superposition of states. Each possible side of the dice is considered a distinct state for the dice to occupy, and until the dice is actually thrown, it exists in all possible states at once. This, by the way, is the same concept that is demonstrated by the famous thought experiment known as Schrödinger's cat, which is both dead and alive until we look inside the box that it's trapped in. Okay, now with this understanding of quantum entanglement, we can actually investigate how quantum mechanics challenges the principle of locality. We can do this with a scenario. Imagine that Bob is on Earth and Alice has used this lovely rocket ship to travel all the way to the sun, each one of them bringing along one of their pair of the magic die. Due to the entangled state of the dice, once Bob has thrown his die, he will immediately know which number Alice's die will land on, even before Alice throws her die. In effect, Bob's dice throw has instantly affected Alice's dice throw. Another way of thinking about this is that the information about the dice throw has been transferred between the Earth and the Sun instantly. To better understand what I mean when I say information transfer, let's look at the probability distribution of a single die. Before observation, this die is in a superposition of states. It could land on any side with equal probability, meaning that it inhabits all states simultaneously. Once the die is actually thrown, this superposition collapses, meaning that the dice has an 100% probability of showing the face that it actually is landed on. So, when Bob throws his dice, the probability distribution of his dice collapses. But really importantly, at the very same time, this means that the probability distribution of Alice's dice also collapses. This collapse into a single state is accompanied by an instantaneous transfer of information across the solar system, something that should not be possible under the principle of locality. And remember, this is very different from what we just discussed when the sun disappeared from the solar system. Recall that in that previous scenario, we saw that the information of the sun's disappearance took 8 minutes to reach Earth. This is because the information traveled at the speed of light, adhering to the principle of locality. So, from what we've seen, this probability distribution collapse for both Bob's and Alice's dice across the solar system seems to clearly violate the principle of locality. This apparent divergence from previously understood theories in physics was shocking and contentious within the physics community. Many famous physicists, among them Albert Einstein himself, believed that something was missing from the theory of quantum mechanics. Einstein, alongside two other physicists named Podolsky and Rosen, proposed an alternative theory. They called this the hidden variable theory. They imagined that there were certain underlying variables within the system that determined its state. Returning to Bob and Alice for a moment, in Einstein's interpretation, the magic dice they threw did not actually have an equal probability of landing on any side before they were thrown. The dice were actually loaded. This means that the result of the dice throws were set before they were even tossed. The way that the weight was carefully distributed within the loaded dice represents a hidden variable, or something that determines the outcome of the throw, but was unknown to either Bob or Alice before they actually made their dice throw. And since the information of the outcome was already within the loaded dice, no information was transmitted instantaneously across the universe, and thus the principle of locality would not be violated. And for decades afterwards, physicists were caught between these two theories, hidden variables theory and the theory proposed by quantum mechanics. In 1964, a famous physicist named John Stuart Bell, who was thinking about this issue, devised a famous theorem that stated that any hidden variable theory would be incompatible with quantum mechanics. At the center of it is Bell's inequality, which would be only valid for hidden variable theories. But if the world was entirely quantum, the inequality would be violated. Thanks to this incredible formulation, physicists could now actually test whether hidden variables or quantum mechanics dictated the behavior of the universe. And that's exactly what three famous physicists did using Bell's inequality. These physicists were Anton Zeilinger, John Clauser, and Alain Aspect. Their experiments, however, did not involve the use of magical dice. Instead, they used pairs of entangled photons, or particles of light. The correlated states that existed were no longer between the numbers that were shown on the dice, but the polarization of the photons, or the angles at which the photons propagate. Zeilinger was the first to use entangled photons in an experiment. Clauser then devised the first experiments for proving that Bell's inequality was violated, and Aspect further improved on these experiments and closed loopholes that physicists thought could still validate the hidden variable theory. Thanks to these sets of experiments, the scientific community was now convinced that they discovered that nature was, in fact, dictated by quantum mechanics, and that no other hidden variables are involved. For these experiments, they were awarded the 2022 Nobel Prize in Physics.